Breaking news, the Curiosity Junior has successfully landed on Mars. MDP Group 27 has successfully landed the Curiosity Junior on Mars. Joining us now live from Mission Control is the brilliant team behind the landing.
Touchdown confirmed. We're safe on Mars.
So Group 27, could you tell us more about the mission?
Yes, of course. For Mission 1, the rover is deployed to conduct a survey of minerals where each has a unique marker on one of four lateral faces. In order to save power, the rover must move optimally to minimize travel distance and avoid collision between minerals. For this particular mission, we successfully managed to obtain 4 out of the 7 samples.
For Mission 2, previously, an unidentified Martian destroyed Curiosity Junior, leaving valuable research data behind. Thus, Curiosity Junior 2 will be responsible for retrieving its predecessor while using an advanced algorithm to trick the Martian into the circle loop in order to escape into the escape pod. We are pleased to announce that Mission 2 was a success with a total time taken of 64 seconds. For Mission 1, I was in charge of the robot's movements. I had to ensure that the movements were consistent and acted accordingly to plan, such that the team is able to devise a proper route. The robot has 6 movements as shown, with each turning movement set to a turning degree of 90 degrees. However, not everything went swimmingly. Some concerns we had were that the robot drifted and that the turning radius was inconsistent. We tackled this by using the PID to control wheel speed and also the servo motor to counter steer. While for the turning radius, we left it up to the algo team. For now, I'll pass on the time to Yongkang.
For Mission 2, we added 2 core navigation features. The features allow users to specify sensors used at directions to either move until an obstacle is detected or continue moving until a detected obstacle is cleared. This ensures precise, sensor-driven positioning for Curiosity Junior 2. During the process, we encountered some challenges. We overcame position overshooting and inconsistent IR sensitivities through rigorous environment testing and manual calibration. We also solved distance tracking issues by using the ultrasonic sensor after trying multiple methods like sensor fusion between the Hall effect encoders and the IMU.
The algorithm team is responsible for finding the optimal path for the robot. Our algorithm optimizes the visit order via a TSP solver by using A-star search for point-to-point navigation. Along the way, we encountered some challenges as well. The hardware constraints kept us from hitting the precise turning displacements our algorithm expected. These inaccuracies accumulated over time, eventually drifting the robot off track. To solve this, we integrated corrective offsets into our algorithm. For instance, instead of a single forward right turn, the robot first moves forward by 4 cm, initiates the turn, then finishes with another 6 cm correction. Doing so kept the actual movement in sync with our simulated path.
We also observed that some generated movement sequences contain redundant commands such as moving forward and then immediately backwards. To address this, we implemented a post-processing step that eliminates unnecessary movements, simplifying the command sequence into only essential actions.
For our image recognition module, we use a custom-trained yellow version 8 model for object detection. The model outputs bounding boxes and the labels and runs in real time on the RPipe. On the left, you can see examples from our training dataset. On the right, these are real-world detection results. This shows that the model is able to accurately detect different samples and the numbers and the actual operating conditions. To further improve performance, we focus on robustness optimization for real-world deployment. We increase data diversity by introducing noise backgrounds, low light conditions, and high exposure images. This helps reduce overfitting to clean data and improve generalizations. As shown on the right, the model is able to maintain stable detection even under challenging environments, such as low visibility and strong lighting. Overall, this significantly reduces the gaps between training and real-world deployment.
Hello, I'm Hui, and I'll be handling the communications, which is a C++ multi-threaded program. The codebase is modular with multiple components handling specific tasks, such as protocols handling messages or device interfaces, ensuring thread safety. Scripts can execute reliably through robust error handling logic, and logging allows for quick bug identification during development. Finally, configs.json defines settings such as camera parameters or timeouts, which allows for quick readjustments without having to rebuild the entire program. And these configs can be tailored to specific environments, such as being indoors or outdoors.
Thank you. Moving on, Yongkang and I will be sharing the revolutionary technologies in our Android app. Firstly, our application offers a modern and powerful UI that allows us to connect to the rover using our patented Bluetooth technology. The application can behave as either a Bluetooth server or client, allowing us to scan, connect, and disconnect our rover all the way from Earth. They also allow us to send strings in a bidirectional manner while storing previously paired devices for easy reconnection. Secondly, our engineers can indicate the rover's initial position, the position of all the minerals by tapping or dragging on the screen, and specify which side of the mineral they should take a picture of. Due to the intensive testing process, I have also implemented a reset and saving functionality that allows us to refresh maps with difficult terrain for continuous and integrated testing. Crucially, once a picture has been taken, the rover will send the data in the form of a number to our application, where it will be enlarged and reflected on our app to indicate that the photo was a success. Finally, the message history can also be viewed so that our engineers can verify that the commands are sent accurately. Thirdly, a D-pad has also been provided to allow our NASA engineers to manually control the rovers for emergencies with alien life forms.
With integrated light, dark, and high contrast themes to ensure visual clarity for all users. We also included a toggle for left and right-handed controls to maximize physical accessibility, alongside a multilingual feature that opens the app to a global audience. These additions ensure our platform is not just functional, but truly inclusive and easy to navigate for everyone.